Welcome to solverfy.
We're looking for an indicator for the titration of CH3NH2 with HCl. This reaction, since HCl completely dissociates in water, can also be written as H plus, or CH3NH2 plus H plus, goes to CH3 NH3 plus, and we don't need the chlorine ions since they will, they're spectator ions, they don't participate in the reaction. In order to find a pH indicator for this titration, we need to know what the pH of the solution will be at the equivalence point, because we want an indicator that will change color at that pH. Because HCl is a strong acid, it will react completely with the weak base, CH3NH2, to form CH3NH3+. So we can now do this problem as this part of the problem as a weak acid dissociation problem. So CH3NH3 plus the water that is in the solution goes to CH3NH2 plus H3O plus. And these are all in the aqueous phase, other than water, which is a liquid. And now we can set up our ice table. Now in order to find the initial value for CH3NH3+, we need to look at our problem and see how much is formed from the CH3NH2 and HCl added at the beginning of the titration, or throughout the titration until we get to the equivalence point. So we know we start with 0.1 molar CH3NH2 and 0.1 molar HCl, which also implies 0.1 molar H plus ions. There's an equal amount of CH3NH2 and H plus, and there's a 1-to-1 ratio in the reaction between them. So all of the CH3NH2 and H plus that we have will be completely reacted. So whatever number of moles we have for either one of these, which are equal, are going to also equal the number of moles of reactants we get out after the reaction. But since we are also adding these two, the volume will double. And since we have an equal number of moles but a doubled volume, our molarity will halve. So we'll end up with 0.05 molar CH3NH3+. So now we know our initial value here, 0.05 molar. And then we start with 0 molar CH3NH2 and 0 molar H3O+. And liquids aren't included in these calculations, so we can just ignore water here. For the change, we react some unknown amount that we can call X to form X of each product, and we'll solve for X later. Our equivalence will be our initial amount plus our change. So for CH3 and NH3+, it is 0.05 minus X. For the product, it's just X for each of them. But look, I just realized I made a mistake here. This should be just KB, not PKB. It's an easy mistake to make, but it really messes up with your calculations. Now, we know that the Ka of CH3 and H3+ is equal to the conjugate base, which in this case is CH3 and H2, times the concentration of hydronium ions over the concentration of the acid at the beginning. So our Ka value is x times x, so x squared, divided by 0.05 minus x. So now we need to find our value for Ka. We have our Kb, and we can go from Ka to Kb using the equation Kw equals Ka times Kb. So our Ka equals Kw over Kb, or 10 to the negative 14th over 4.4 times 10 to the negative 4th. This value here we got from here in the problem, and the value of Kw is a constant. This gives us a Ka of 2.27 times 10 to the negative 11th, which again is equal to x squared over 0.05 minus x. Now, in order to make solving for x a little bit simpler, we can try to make this assumption that this x here is so small that it won't affect whether we actually subtract it from 0.5 or not. So we can assume x equals 0 and solve for x that way. So x squared equals 2.27 times 10 to the negative 11th. And we can make this assumption as long as we check at the end that it's a valid assumption. So if x squared is 2.27 times 10 to the negative 11th, then x is the square root of that, which is 4.8 times 10 to the negative 6th. Now to quickly check that assumption that we made earlier, if we have 0.05 and subtract 4.8 times 10 to the negative 6th, our answer is still going to be 0.05 to two significant figures. So we know that our assumption is valid. Now we have a value for x, which means we have a value for our concentration of hydroxide ions at the end of our titration, or at the equivalence point of our titration. So now we can solve for the pH. pH is equal to the negative log of the concentration of hydronium ions. So it's equal to the negative log of our value of x, which is 4.8 times 10 to the negative 6th. And this is 5.3 for our pH at the equivalence point of this titration. We're looking for a pH indicator that changes color at a pH of approximately 5.3. The indicator called methyl red has a pH range of approximately 4.8 to 6.0, which makes it the perfect indicator for our titration here. Now, if we're doing a titration of HI with KOH, this is a strong acid, strong base reaction, which means our equivalence point will be when the solution is at a pH of 7. If you don't have this memorized, you can write out the reaction and see that it will form water and I plus and K plus, all of which are neutral in solution. So we have a neutral pH, which is a pH of 7. This means we want a pH indicator that changes color at a pH of 7. Bromothymol blue has a pH range of approximately 6 to 7.6, which makes it a perfect indicator for a strong base or strong acid, strong base titration like this one.